We were about to see it, you know?
Wait, can you show us with 1/2 x file we're looking at?
Ooh. But you know, the really beautiful thing here is if you're interested, you can easily study all possible curves of this form, right? Whee! Ooh. Funky. Neato. All right. Okay, so let's see here. What were we doing? Oh, the one I did earlier. R equals to the square root of 3 divided by, what did we got? Am I missing a square root downstairs? Plus, what was it? What do you mean, question mark? Parenth. Oh, yeah, okay. Huh, that's funny. That was, we were just looking at like the sine of cosine theta there, something like that. Let me turn off the others. I said, be gone. I said, be gone. Whoa. What happens if I put a minus? Well, let me try to do both. Yeah, I need to do that too. Oh, they're the same thing. What if I put my, oh, if they put, so you notice the plus and the minus? This equation has what's called a symmetry through the origin, which means that if you replace r with minus r, you have the same set of points in the solution set. So actually, without loss of generality, I can drop the plus minus. And this is, in fact, a polar graph. It's not graphs. I didn't need the S. But I didn't know that until I thought about it more. And you said to zoom out. What do we got here? It's probably a hyperbola. So, but anyway. Let me show you a couple more graphs I already have worked out. So we'll look at them together. These are in the notes that I posted here. The last announcement. Do you guys actually get the announcement? I mean, it depends on whether or not you have notifications turned on. I just had a student in my online class ask me about, like, what's on the test. I teach a abstract algebra online thing, and no, this is I don't know where they are, but this is the Liberty class, and I'm like, why? I just made an announcement where I go like, you need to be responsible for these things on this next test, you know? Did you see my announcement? Like, no, I didn't see your announcement. Like, you know, we used to have this thing called Blackboard, and like I would say email to students, and it did. I miss that. Oh, it's good that I did this. So in my notes, I've decided, rather than using, okay, so listen, you guys don't typically have colored markers and stuff with you, right? So the approach I'm taking in the notes may or may not be tenable for you, but color coding can be very labor saving here. Like you got choices, right? Either you need to like put down a bunch of labels to track what you're doing, right? Or you need to come up with some sort of like color coding scheme to track your work. I found color coding to be very helpful in graphing. So like here's one, r equals sine 3 theta. So r equals sine 3 theta, here's the r theta graph of it, all right? And so this is in radians, and I'm too lazy to make it into pies, my bad. But obviously this is what, like what is pi over 3? 3.14 divided by 3 is 1.05-ish. So this is pi over 3, right? This is 2 pi over 3. This is pi. That's all you need to look at in terms of the graph of sine 3 theta. And so this is going from 0 to pi over 3. What is pi over 3? Pi over 3 is a ray from the origin at 60 degrees. So as you look at the graph here, you see, whoa, well, it is what it is. So you're going from 0, which is this guy, to pi over 3, which is, oh man. I gotta find like a little bit less aggressive a green laser. I guess I could take it to Convo Friday.
I think that's a great idea.
No, yeah. So you'll have Dr. Sperano for the rest of the semester. I'll be in the pokey. See, they'll put me in Liberty Jail. Where is that? The loopties. Anyway, so this is 0, this is pi over 3, and that's that, right? So it goes to its maximum in the middle, which is pi over 6, right? So I like to, when I'm actually doing this by hand, I draw rays at like pi over 6 and pi over 3, all of the interesting angles, and that informs how I draw the petals. Like that's the nice way to do it, okay? If you look at my solutions from yesteryear, you'll see that. So this blue node, that's negative r, right? So technically that's going from pi over 3 to 2 pi over 3, which would geometrically just be here to over here, right? Well, to over here, 2 pi over 3. So pi over 3 to 2 pi over 3. It's this wedge up here. But what's the deal with the blue part? Negative r, so it flips it to the diametrically opposite points. Like I said, I can't avoid the negative r, it just does it, yeah. And then over here, 2 pi over 3 to pi, which would be here to there, and that's that. And then you just start looping back again. Now, how do you, there are graphs where you don't loop, like this. If I put an e here, like 2.71, the irrational number e, it will never be the case that this graph comes back where it was geometrically in the same fashion. It just keeps processing, if you will. All right, it's not quite where it started in its cycle before, and it just keeps. And if you if you go to, so here's for basically two sort of, I would say you want to say 2 periods, but it's not quite accurate, right? Because periodic motion, it has to do what? It has to start over again in the same exact fashion, right? But we do this in mathematics and engineering. We talk about things being periodic that aren't genuinely periodic. All right? Like the period of this is 2 pi, but it's not technically speaking periodic. In a generalized, somewhat fuzzy sense of periodicity, it's periodic, right? Because it's repeating, but it's not exactly the same. But anyway, if you go on to, instead of this is 2 cycles, this is 50 cycles of this thing. By then it's, you know, and you know what happens to this if we go on further, right? It just colors it in.
Does it fill up all the points though, or are there still points there?
It will densely, like you can, let me say it carefully. If you pick any point in the unit disk, all right, you can go sufficiently far out in that graph to get as close as you want to that point. In that sense, it's dense. You can always get arbitrarily close to any point. So, I'm not sure that it actually reaches the point. I'm not sure about that. But it definitely densely, for sure, for certain, it's dense in that sense. Here's another one. If we graph cosine 2 theta, here's my color-coded graph, right? And I'm really just interested when r goes to 0, because r going to 0 pretty much tells me I'm going from one phase of the story to the next, right? So like, there's this red petal, which corresponds to this hump. There's this blue petal, which corresponds to this. But now notice that here we're going from, what angle is that? 2 theta, so this would be pi over 4. Pi over 4 to 3 pi over 4, I believe. So pi over 4, to 3 pi over 4, is this, right? And yet, the blue is down here, why? Negative, right? The green is positive, r, so it's geometrically where it's supposed to be. And then the black here, again, is negative, so that would be going from Oh, I got to think. Well, anyway, it's negative, so this would be supposed to be down here, but it flips it up over there. All right. Here's another one, 2 plus cosine 2 theta. Now this one's interesting in that there is no place where the radius is 0, right? You don't have to have 0. If you don't, you have to kind of adopt a different approach. And so what I did was I said, well, I'm going to look at, like, I'm still going to look at this color coding scheme, but I'm going to notice that it's basically, let's see here, you're going, it's basically based on radius 2, right? At radius 2, whenever I cross this line, so like this red line, this red hump here corresponds to that because it's going from, see, this is why labels would be wonderful if I had labels here, but this is, I think, pi over 4 to minus pi over 4. That's this, pi over 4 minus pi over 4, all right? So that's this red business. Now, the blue is closer to the origin, right? Because you're going from radius 1 down to radius 2 rather than down to radius 1. This is pi over 4, this must be pi over 2. So pi over 2 is one of the places of closest approach. As you can see, pi over 2, closest approach at 1, radius 1. And, you know, down here, this would be, I think, 3 pi over 2. And so 3 pi over 2 is, you'd say like, well, 3 pi over 2 is radius, yeah, so this graph is nice. Like, we don't have to use the negative radius interpretation doesn't come up in this one, right? It's all positive radius, so it's just that. I mean, so if you want to graph a peanut, there you go. Let's see if I got any more for us. Oh, look at this one. This one's interesting. Again, these are all in the posted notes. I just wanted to talk through them with you. Here, I've got r equals minus 1 plus 2 cosine 2 theta. The graph in the r theta plane looks like this. So we've got these positive and then these larger negative nubs. And so that, goodness gracious, I think, man, I can't remember. I think that's pi over 4 still. This is still like based on pi over 4. I think the color changes are happening like plus or minus pi over 4. Where is that? Oh, I have it up here. My bad, it's not that. It's plus or minus pi over 6. And this is 5 pi over 6. And I think that's 7 pi over 6, if I remember right. So you get these little nubs here, and then you've got the larger petals like that from these. And then this one's just kind of weird, and you know, theta sine theta, that's different. So the graph of theta sine theta looks like this. It's like a sine graph, but it keeps growing as theta grows, right? It's sort of a modulated sine graph. And there I graph the little loop, and here is red, and the big loop is blue, like that. So anyway, I'll tell you what would be a tricky question, would be to find the area between these loops. The reason that would be a tricky question is that the same equation is defining both loops, and it is genuinely polar. So if I was to try to do that, I would want to rewrite the equation for either the inner loop or the outer loop in terms of the angle of the other loop. So I'd have to stop and think about that. But basically, you know, I don't know if that's nice. Is that nice? What's that? Oh. Oh yeah, yeah. You guys have got a good idea. So you're just like integrate from here to here, and then subtract the integral from here to here. Yeah. Okay, that's better. Thank you. Yeah. I'm sorry. I've been thinking about other regions where we have an inner radius and an outer radius, and we calculate the area in that regard. So I had forgotten about that idea, what you guys just said. Anyway, we'll be talking about that soon enough, but not tomorrow. Tomorrow we have a quiz. So, and then class will end a little bit early. So, yeah. I mean, you can. Yeah, I want you all to get good seats. That's right.
Here tomorrow.
Oh.
Eagle Scout has a retreat, so I can't get out of it.
Oh, okay.
'Cause I totally would rather just take your test or quiz or whatever.
Uh-huh.
It's so much more than go to Hideaway for a retreat.
Ah.
When do you want me to make that up?
Will you be here tomorrow at all?
On campus, I'll be here for like 2 hours.
Is that later in the day or earlier?
Yeah, it'll be. We're supposed to get back around like 1:32ish.
Okay. We'll
And
just,
then I gotta leave campus by 4 o'clock.
if you could just come find me. 1:32. I have office hours from